All right, so this is the last day we're going to meet. Your final exam is on December 9th, I believe. Yes, Tuesday of next week. And we will meet at 11 a.m. right here. The test will go till 1:45 p.m. That's how much time you have for the test. All right. And the test is in some sense cumulative. When we look at the review in a little while, you'll kind of get an idea of what to look at. Cumulative starting, looks like about chapter 7. So that's like applications of integration and on. So it's really 2 chapters, 7 and 8. It's not going to cover all the techniques of integration. Okay? So today what we're going to try and look at are 2 sections, or actually 2 topics in chapter 9, parametric curves and polar curves. So I'm in chapter 9 here. Parametric and polar curves. So let's start with parametric, all right, and then we'll get to polar. We'll see how far we get. I want to try and leave myself about 20 minutes at the end. So if you see me getting close to the end, like about, what, 12:20, cut me off, all right? Parametric equations, all right, let's start here. So when we have a relationship between 2 variables, something like y equals x squared, right? We usually would convert that into maybe a functional notation. We'd say, all right, f of x is x squared. In other words, the y value can be determined as a function of x, right? Y is a function of x here. I'll even put that here. Y is a function of x. So that if we look at the domain and the range of this function, the domain of the function, or the things that go into it, right, would be the x values. And then the range of this would be the y's, right? And so what we did is we said, all right, can we visualize this relationship? Like we know that if we plug in 0 for x, we're going to get 0 for y. If we plug in 1 for x, we're going to get 1 for y. If we plug in -1 for x, we're going to get 1 for y, right? So can we visualize the relationship? And we realized that, you know, we can. What we do is we draw an x and a y axis like this. And let's just keep in mind that the domain here is our x-axis, right? And the range is going to involve the y-axis. So we can actually see in the picture both our domain and the range at the same time, can't we? So we take an example, something like if x is 0, y is 0, we look at that as an ordered pair, 0, 0, right? That's our x and our y. And then we plot that as a point on the graph. The x-coordinate is whatever we plugged in, the y-coordinate is whatever came out due to this function, right? We plug in 1, it spits out 1. We plug in -1, it spits out 1 again, right? And if we draw all of them together, you know, all the possible ordered pairs, then that parabola represents the relationship between those 2 variables. The idea of a function, though, was that for every single input, right, it could only go to one place, right? So for every x I plug in, there's only one y that can come out. I can't plug in an x and get 2 y's, correct? So let's look at that versus this. What if I give you a relationship and I say x is y squared? Well, here you could write f of y is y squared. And then in this picture, what is a function of what? Which variable is a function of which variable? X is a function of y. You give me y, I can give you x, right? So here we say x is a function of y. And then I could go through the whole thing again. The domain here is what? The y values. The range here are the x's. So everything's just kind of switched, right? And so when we graph it, we still have the x and y axes, but they're flipped now. My y is my domain, right? And my x is my range. And if I were to pick values of y and determine what the x's are, we would get a parabola that would actually open up this way instead, right? Now, the importance of this, and just noticing this subtle difference here, is the fact that if I graph this right here, is that a function? Yes? Okay. Is this a function? We just said it was. It's a function of y, right? So when we talk about functions, we actually have to understand now, like the vertical line test was great in college algebra, because we always assumed x was the variable being plugged in, right? X was the domain, and y was what was coming out. So this fails the vertical line test, so therefore we usually say it's not a function. But it truly is a function. It can be represented as a function, but a function of y instead. X is a function of y. Make sense? So when we start talking about functions now, we really want to understand that the vertical line test is kind of off the page now, because it really matters what variable we're saying is a function of which other one. Understand? Okay, so now let's see. Get back to this idea of one input gives you one output. Here, if I plug in, let's say 2 for y, what does it spit out? 4. So if I go up 2, it's going to spit out an x of 4, right? Yes? Okay. Now, I plugged in 2 for y, right? X got spit out to be 4. If you come up here and you say, and I tell you up here that y, okay, y is 4. Can you tell me what x is? It could be either 2 or negative 2, right? I mean, that's the whole idea here, is that to say that y depends on x means if someone gives you x, it's going to go to exactly one place. But if someone gives you y, you may not be able to determine exactly where it came from. In this case, you can't. If I give you y, you cannot tell me exactly where it came from. You can narrow it down to 2 things, but you can't tell me exactly. So a good example of this would be, let's say you take this problem here, and you say, I want to solve it for y. You take the square root on both sides, right? So you get something like y equals, the square root of x is that, but you have to do plus or minus when you take the square root, don't you? Now, could you look at this as being a function of x? Can you define a function of x to be plus or minus the square root of x? Is this possible? Can I write f, a function of x, to be this? I'm going to have 2 outputs, right? If you give me a number like 2, or let's say 4, if you give me 4 here, it's going to spit out 2 different things, right? So this cannot be written as a function of x. It fails what's required to be a function. One input, one output. Yes? So that's why I could say x is a function of y, but I could not say y is a function of x in this problem. Make sense? Okay, so let's look at the challenge that we have here. I wonder, on this example, I'm going to give you the graph. Here's 1, here's 1, here's negative 1, here's negative 1. Here's a graph. Sorry, not my best circle. Actually, it doesn't look too bad up there. What are your thoughts here? Can we represent all of those points where we can write x as a function of y or y as a function of x? Yes or no? Why or why not? Okay, so you would have to break it up into two functions. Just like in the previous problem, you could look at this and break it up into where one function is positive root x, the other one is negative root x, right? So when you draw a positive root x, it draws the top of the parabola. And when you draw negative root x, it draws the bottom, right? But that's two distinct functions. They're not the same function, right? So yes, I agree with you. You could draw this possibly by creating two or possibly more functions and just draw it piece by piece. I agree, but can you do it with one function? Well, if we're gonna sit here and say y has to be a function of x, right? Y has to be a function of x, then it has to pass the vertical line test. And it doesn't, right? This x value goes to two different places, doesn't it? So that I couldn't do y as a function of x. Could I do x as a function of y? You'd have the same problem because now you would have, I guess you would call it a horizontal line test, which is always, you use the horizontal line test in college algebra to see if a function has an inverse. But you can also use a horizontal line test to check whether or not you can look at x as a function of y. And you wouldn't be able to also because you would hit in two places, right? Is this making sense? So it appears at this point that writing x as a function of, writing y as a function of x is not going to happen, right? And writing x as a function of y is not going to be possible either. But it's a circle. We got to be able to draw a circle using a function, and that's where the whole idea of parametric curves comes from. See, when we've drawn curves here, we've always wanted to try and show the domain and the range at the same time, right? We want to draw a picture where you can see the domain and the range together, right? Maybe the domain's the x-axis and the range is the y, or the other way around. The domain is the y and the range is the x. But why do we have to draw the domain and range together? Why can't we just draw the range and let the domain be somewhere else? I know it's kind of odd concept, but just watch what I'm going to do, okay? The idea of a parametric curve or parametric equations is what we're going to use to be able to draw something and not have to worry about this whole vertical line test anymore, right? It's pretty much going to go away. So a parametric curve, I can't spell today. Yeah. Is given by two equations. The first one is x equals something, we'll talk about it, and then y equals something. So what we've been stuck with this whole idea of vertical line test and horizontal line test, the problem is that we keep on trying to connect x to y, right? We keep on trying to make the relationship between x and y instead of letting just x and y be whatever the hell they want to be, and then trying to figure out how I can create x and create y using a single function and not worry about connecting them together necessarily. So I need to figure out what function, I will call it f, and of some other variable which we'll call t. X is some function of t. I don't know what it is. And then the y coordinate is some other function, g of t. And t is in some interval, right? It is the domain, basically. This is the domain variable. See, what I've done is I've released x from being tied to y. I've said to figure out x, the only thing I need to know is t. And to figure out y, the only thing I need to know is t. Now, what happens and how these change are completely independent of each other now, right? Does that kind of make sense? So I would like to now see if there's a possible way I can draw that circle with this idea. So let's go and take a look at this circle for a second. Back to this example. This unit circle that I had, let's take an arbitrary point on this circle. Everybody agrees that that arbitrary point has an x and a y coordinate. Yes? Has an x and a y coordinate. What I need to do is figure out what that x coordinate is and what that y coordinate is, and not rely on the relationship between each other. So we all know that if you look at a unit circle, right, or any circle, then this point, you can draw a line from the origin to that point, and that would have some fixed radius, right? In this particular problem, it would be 1, wouldn't it, because it was a unit circle? So that would be 1. And then, if I construct a right triangle, the distance from here to here is equivalent to the x-coordinate, and the distance from here to here is equivalent to the y-coordinate. And we have from pre-cal that if you know the sides of a triangle and you know the angle inside, there's some relationship in there, right? Like this x and this y coordinate are going to be completely determined by that angle. If I change the angle, it's going to change my x and y. So somehow the x depends on the angle and the y depends on the angle. Yes? So I'm going to call that angle t, because t, I mean, I could call it theta if I wanted to, but I'm going to call it t because t appears to be the thing that will dictate what x and y are. So can you give me the relationship between t and, let's say, x? Give me a relationship between t and x. Cosine t is x, right? Cosine is adjacent over hypotenuse. And then the other relationship is what? Sine t is y. And so what I have actually come up with here are two parametric equations. I have come up with an equation for x. I have come up with an equation for y. They both depend on what we call the parameter, which is where the whole idea of parametric comes from. They both depend on the parameter t. I change t, I'm going to change my x, I'm going to change my y. And if I change t, I should move myself around this circle, shouldn't I? Okay, so this is it. These are the parametric equations. But I had to have some knowledge of a circle to do this, right? I had to be able to have some general knowledge of a circle and the way things work out in order to be able to draw this circle. Yeah? Okay, so let's just show that this will draw the circle. And the best way to show it is to plug in some values. So I'm going to plug in some t's and then let's see what it spits out. So you know how we used to do a t-table like this? And we do like x and y? Well, this time we're going to be plugging in t, right? And it's going to be spitting out what? X and y. So it's actually going to be spitting out an ordered pair. I plug in the domain is t, right? Domain is t. I'm going to put d above that for domain, right? And the range of it is what? Ordered pairs, right? You plug in a number, it spits out not a number. You plug in a number, it spits out an ordered pair. That's fine. It's okay for that to happen. We just haven't done it a lot, right? So let's plug in some values of t. How about 0? So if my angle is 0, right, or if t is 0, you get cosine of 0 is 1, and sine of 0 is 0. So you were at the point 1, 0, aren't you? Okay. Let's plug in some other common angles. How about pi over 4? At pi over 4, it's root 2 over 2, root 2 over 2. So cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2 also. One of the next common angles, pi over 2. What's cosine of pi over 2? 0. Sine of pi over 2 is 1. Okay, so on my picture, I think what I'm going to do is I'm going to draw the 3 points that we just did, and I'll highlight them in yellow. So I have 1, I have 2, I have 3. We just found those 3 points. And all the t values between 0 and pi over 4 and pi over 4 and pi over 2, if we plug those in, we would draw that entire first quadrant of the circle, right? Now, would you agree with me at this point? I don't have any issues with the whole idea of function, one input, one output. I mean, every input went to one output, right? Okay. Now, back in the other picture when I first started this, I said, look, we're going to fail the vertical line test or horizontal line test. So I'm actually going to maybe start having some issues when I get into the second quadrant, because that's where it would have failed this test, right? But I'm going to show you it's not going to matter, right? It's just not going to matter. So let's start plugging in some more values. How about 3 pi over 4? So if you plug that in, you'll get negative root 2 over 2, positive root 2 over 2. And that's this point right here. Highlighted that in green. Now, why is it that this was an issue earlier? Because what happened is we had 2 y coordinates, right? I mean, sorry, if I plug in a y here, like if I look at the y value here, there's 2 x values for it, right? 2 different x values for the same y, and that's where we had the problem. Or here you could say that we have 2 different y values for the same x. Here, even though these are directly across from each other, to draw this one, what do I have to plug into the function? Pi over 4. To draw this one, what do I plug in? 3 pi over 4. Completely different numbers, right? One of them comes from t is pi over 4. The other one comes from t is 3 pi over 4. They don't both come from the same place, do they? And so we don't have the ideas here is that one point in the t is going to one ordered pair. It's not going to 2 different places. And as I go around this entire circle, the whole thing is going to maintain that property. So let's just keep going. Do I need to really go through the table? Okay, so it goes here, and then it would go here, and then here, then here. And so each of those points are drawn. That means everything in between them is drawn. Now, this is interesting. What if I get back to here? What about 2 pi? 2 pi gives me what? 1, 0? Is that a problem? That's right. Now, it's kind of like my function is drawing over itself now, right? But it's not violating being a function. To be a function, every input has to go to one place. It's okay if the function goes to the same place, right? You could have back in college algebra a function f of x equals 4. That's a function, right? For every input, there's one output. The fact that it's the same output doesn't matter. You just can't have something go in and go to 2 places. Make sense? If the input goes to one place, it's a function. Yes? And the problem we had here was that if you wanted to say x was your input here, right here, if you try and say x is your input, then if you say 16, then where does that go to? Well, it comes from 4 or negative 4. So it's one input, 2 outputs. So you can't say it that way. Here it's not going to matter. Now, the drawback to this is that even though you can visualize the range, right? This is the range of the function that we're looking at. You do not see the domain in the picture. The domain is like a clock that's running in the background, right? So that's what we give up in this, is that we don't have the domain up there also. Make sense? Now, with this idea, we can draw just about anything. I mean, not everything, but a lot of stuff. So let's say I wanted to do this. Y equals x squared. I want to do this, but write this as parametric. Curve. We did this back when we were doing integration, all right? Showed a couple of y'all how to do it on your calculators. I want my x to be something and my y to be something, right? That's what I'm looking for, some function of t. Now, this equation, we know graphs a parabola, right? So we know that we can look at this as f, right, is a function of x, right? Or y is a function of x. So since y is a function of x, the independent variable is x here, right? We could treat x as the independent variable. So we could treat x as the time, right? We could just let x be the time, t. So let x be t, and then if x is t, then what is y? T squared. Right? According to this, if I'm trying to draw this, which we already know is a parabola, we know that y here is a function of x. Anytime that y is a function of x, you can replace the x with t, and then rewrite y, replacing all the x's with t, and then if you do that and plug in t's, it should draw the exact same thing. Do y'all remember, those of you who I helped on the calculator do this? This is what we did. And you could do your ordered, they're not ordered pairs anymore, but here's t, and then here's your x, y. So if t is 0, what do you get? 0, 0. If t is 1, what do you get? If t is 2, you get 2, 4. If t is negative 1, you get negative 1, 1. If t is negative 2, you get negative 2, 4. And I claim that if you graph those, you're going to get the exact same thing. All right? But again, the difference is that the domain is not on your graph. The domain is in the background. How could you do this? If I wanted to do x equals y squared. What could I do here? Okay, so I realize that this is this, right? So I know I can write x as a function of y. I can't write y as a function of x. So I need to come up with my two equations. Since x depends on y, y is the independent variable, therefore I can replace y with t, and then rewrite x in terms of y, which would now be t squared. So it's the opposite of what we just did, right? And then if you do a little thing over here, here's t, here's x, y, and plug in these values, you should draw that parabola. But it doesn't violate being a function. Now, why is this good? Because what is it that we've been doing in this class with functions? Integrating them, right? Finding areas under curves, finding arc lengths, things like that. Well, I think we would all agree that this circle has tangent lines on it, right? So derivatives, right? We could find that, remember, derivative is the slope of a tangent line. Do you agree that at every point here there's a tangent line? Okay, so we should be able to find it. I mean, this is calculus. There's an area here. We should be able to find that area. There's actually an arc length to this. So we should be able to find that too. But the question is, how do you find the derivative? How do you find areas? How do you find arc lengths if it's not a traditional function? Well, what we do is we convert it to parametric curve, and then we have calculus on the parametric curve instead of to the traditional function. Make sense? All right, so let me see here. There's a couple of things I had put together here. So this is just a traditional function, and what I'm showing here is that the green dot is our domain, and the red dot depends on that green dot. So as the green dot moves, for every x there is some corresponding y, right? This is our traditional function. Domain's there, range is there. This, we had, what the heck is going on here? Is that green dot our domain? It can't possibly be, right? Because then for this x, I should have some y's up here. So what the green dot is the time in the background. I'm trying to show you it's the time in the background. So for this is time 0 for this particular, there's time 0. Now, I didn't write it down here, but the parametric equations for this are x equals t squared minus 2t. The other one is y is equal to t plus 1. right? So that blue curve is this parametric curve. If t is 0, where would I be? 0, 1, okay, at that ordered pair, you see? So at t is 0, so I'm trying to visualize the time as being on my x-axis even though it truly isn't the x value. This is like time down here. And then as time moves on, when I get to 1, right, where should I be? Well, 1, take away 2, so -1 and then 2. So I should be at -1, 2, you see? So I'm drawing this thing with parametric curves. Here's my circle. I can draw my circle. Now here's my time. I tried to show my time again. So that's 0, and then as time goes on, we're drawing the curve, we're drawing the curve, we're drawing the curve, coming around and back here. And if I keep going, I just keep on drawing the curve on top of itself over and over and over. So what we usually do is we like to restrict the domain. Like, let's just look at this and restrict it between t between 0 and 2 pi, and that'll just draw that circle one time. Same thing. Now here's something interesting. A wheel that's rolling, okay? You have a wheel that's turning, right? You're driving down the road. You've got a nail stuck in your tire. That red dot is the nail. That's the path of the nail. Okay, the blue curve is the path of the nail. Right, so that's what something looks like when it's going around on a tire. This is the path through space, like this. It's pretty violent, isn't it? I mean, that's a pretty violent. I mean, you would think if you're on a circle spinning, everything's great, right? But this is a pretty. I mean, look at this. You're moving, and all of a sudden, there's like almost like this instantaneous change in direction, isn't there? From going down to up. I mean, that's. You know what I'm saying by violent? I mean, it's a major change in direction. It's not like when you're on a. It wouldn't be like spinning around a merry-go-round where you're just going in this motion like in a circle, right? If you're stuck to the tire, you are actually going in these boom, 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 boom. That's what it would feel like to you. It'd suck. So this right here, this curve can be drawn with a parametric curve, parametric equations. The parametric equations for this, it's called the cycloid, by the way, are x equals t minus sine t, and then y equals 1 minus cosine t. And you could actually prove this with some geometry. You could actually come up with this. I think the book goes through it and proves how this comes about. But this right here draws that. All right? You believe it? Yeah. You could plug in values of t and you would see it would do it. All right. So let me see what else, if there's anything else I want to talk about. We got to get into some of the calculus behind this. Oh, here's another one. So, yeah, so this one is just another example of, oh, slow it down, slow it down, slow it down. I'm going faster. There we go. So what's cool about this is you can see what happens, you know, at t equals 0. At t equals 0, here you are, right? And then as I draw this, here's my time. You know, this is what it's drawing. You can kind of see it up there. Here it is right here. Here's x. That's x right there. Sine t plus 1/2 cosine 5t plus 1/4 sine 13t. And then the y value is cosine t plus 1/2 sine 5t plus 1/4 cosine 13t. And you could tweak these and change it, and it would change how it looks a little bit, and, you know, whatever. But I guess the idea here is that you can start to get some curves that look really symmetric, that start to look like things in nature, who knows, whatever. I mean, it doesn't have to be this complicated looking, but that just gives you an idea of how complicated you can get. Like, it can start getting pretty pretty nice. I mean, you know what I'm saying? The curves are starting to look fun. I have another one. Okay, this is just to show you, here's another one, where at every point on this curve, you have a tangent line, don't you? Now, what we would run into here is that if we were trying to look at this as a function, right? Classic college algebra function, or even Cal 1 function, we would say, all right, what's the slope of the tangent line there? We'd say, you know, what's y prime? And then we come up with the answer, and then what you would have to do is plug in a value of x in order to determine that slope, right? Well, the problem here is that for this curve, if I plug in an x, it's actually one of two different points, isn't it? If I plug in a value of x, it's up here, or it could be down here. The slope of the tangent line up there is different than the slope of the tangent line down here, isn't it? And so if we're going to talk about tangent lines, then we're going to need to make sure that we understand that we will have to, in some sense, concede to the idea that to find the tangent line on a parametric curve, I will have to know exactly what point I'm at, which means I'm going to have to know the t value, right? Because for every t, there's a point, right? But the idea is still there that we could find the slope of the tangent line. In fact, we could do it here, right? There's your slope of your tangent line. So we've got the tangent line is, let's talk about this tangent line. The tangent line is positive. It's 0. It is infinite, undefined. It's positive, 0, negative, infinite, positive, 0, right? We're going to do this problem in a little while. We're going to figure out when the slope of the tangent line is 0. We're going to find out when it's undefined. We're going to find out that information, right? But we need to figure out how are we actually going to find the slope of the tangent line, right? How are we going to do that? All right, I hope that's enough just to get you motivated visually as to what's happening here. So with these parametric curves, we have the idea of derivative is here. So if you have x equals some function of t, y is some function of t, some other function of t, and t is restricted between a and b, if this right here draws a curve which is traversed one time, then this is like a curved segment, isn't it? This would be like a segment of a curve. What I'm doing here is I'm just helping you realize that if you restrict the domain of t so that when you draw it, you only traverse that curve one time, then you've drawn a curved segment. An example of this would be if I just write x is cosine t, y is sine t, right? And I don't give you a restriction on t, what's that going to draw? It's just going to be a unit circle, but it's infinitely many times on top of itself, right? So if I restrict it and I go t is, let's say, between 0 and pi instead, now I'm going to draw the top half of the circle, the unit circle, right? So I've drawn a curved segment. This will become important in a little bit when we talk a little bit about how you find areas. Although I don't even know if I'm going to have time. All right, so let's talk about the derivative. derivatives of parametric curves. We always wanted to know what a derivative was, right? We always were interested in that in Cal 1. We always wanted to know what y prime was. And when we said y prime, what we really meant was dy dx, right? dy dx? Okay. So for us, do you agree that, let me see how I want to write this. Does that make sense to you that this would be true? It's almost like these are fractions and you could just reciprocate them. If I flip this one up, right, wouldn't I just get the dt's to cancel? And it would be dy dx? But the reason why I've written it this way is because we know with the parametric curve that y is a function of t, isn't it? And so I can take the derivative of y with respect to t. And if x is a function of t, I can take the derivative of x with respect to t. And so this is saying that if I want to know the derivative of y with respect to x, so the change in y with respect to x, the slope of that tangent line, then I just need to be able to take the derivative of each of the equations that I have for x and y and then just create the ratio of those two. It's a very simple formula. There's nothing really to it. We just have to be careful that the derivative of x with respect to t is never 0. So let's do an example here. Find y prime for unit circle. I would like for you to give me an equation or something where I can determine the derivative, the slope of the tangent line on the unit circle. Now, if you were in Cal 1, you would kind of be stuck a little bit because you would realize that for a circle you can't write it as a function, right? So you could say, oh, maybe I can take care of the top half and then take the bottom half separately, but you couldn't do it all at one time. Now we can do it all at one time. Okay, so what we need to be able to do is first come up with the equation, right? The curve equations, which we already did that, right? We know that x is equal to cosine t. We know, comma, I'm going to put y is equal to sine t. And so let me find dx dt real quick. What's dx dt? Derivative of cosine t, negative sine t. And then what is the derivative of y with respect to t? Cosine t. Yes? So what is y prime? It's dy dt cosine t over negative sine t. That's it right there. Didn't I say a second ago that if we are going to try and find the slope of a tangent line on a parametric curve, we will have to kind of surrender to the idea that we're going to have to know the exact point? But to know the point, we're just going to need to know t? Well, then our derivative should depend on t, shouldn't it? And it does. So give me a t. Someone give me a t here. If t is pi over 2, right? If t is pi over 2, where are we on the circle? We did that earlier. What point are we at? We're at the point 0, 1, right? So we should be here. What should the slope of the tangent line be there? 0. Well, plug in pi over 2 into this, and what do you get? At t equals pi over 2, we get that y prime is cosine of pi over 2 over negative sine of pi over 2 which is 0 over negative 1, which is 0, which matches the idea of that being true, right? The slope of the tangent line up there is 0. All right, let's do something a little more interesting than that. How about this point here at pi over 4? How about at pi over 4? It should be whatever cosine of pi over 4 is. What's cosine of pi over 4? It's root 2 over 2. What's sine of pi over 4? Same thing, but there was a negative down here, right? There was a negative right here, so it's negative root 2 over 2. And that's just negative 1. Does that make sense that it would be negative 1 there? Yeah. You follow this? How about at 0? How about at t is 0? It's undefined, right? Well, what's the slope of a vertical line? It's undefined, right? So that makes sense that it would be that case, wouldn't it? So at t equals 0, y prime is undefined. And that's because at 0, which is this point here, we have a vertical tangent line. You tell me. What's cosine of pi? Negative 1. What's sine of pi? 0. So you get undefined again. Okay? It's not too bad, right? I mean, taking derivative of parametric curve is not that bad. It's just derivative of each piece, right? Each equation, sorry. Each function, you could say each function. All right, so let's take that cycloid problem. We have that cycloid that I put up here, right? This was it right here. It was x was equal to t minus sine t, and y was equal to 1 minus cosine t. Right? This is our wheel spinning, right? It's that nail in our tire. I'm just thinking about this. Get this back here. Oh, wrong one. So let's say this nail's going here, right? All of a sudden, the nail, maybe it's not a nail, maybe it's a rock that's stuck in the treads, right? The rock is stuck in the treads. So if this thing lets go right now, right, the rock comes out, which way is it going to fly? It'll fly in the direction of the tangent line. That's the way it's going to go, right? Won't it? As soon as it's released from the tire, it'll go in the direction it was headed at that instant in time. That's all this is. This curve is really just, right, you've got the circle, draw a perpendicular down to the origin, right? That's what that tangent line is. But see, the circle's moving, so that tangent line's always changing. Okay, let's try and figure out what the slope of this tangent line is. What is the formula for it? So y prime would be dy dt. What's dy dt? You're doing dx dt. That's all right. So we're going dy dt over dx dt, which for us is derivative of y with respect to t, which you said was what? Sine t over the derivative of the x with respect to 1 minus cosine t. Now, my questions are, when is y prime, or when is tangent line horizontal? And when is it vertical? So if I want to know when the tangent line is horizontal, that's the same as saying when is the derivative what? Equal to 0, right? Horizontal line has a slope of 0. So to say I want to know when the tangent line is horizontal means I need to know when this fraction is 0. When is that fraction 0? The only time a fraction can ever be 0 is what? When the top is 0. So for the horizontal part, all I need to do is figure out when sine of t is 0. So when is sine t 0? 0 and pi, yes. Sine is 0 here. This is back to pre-cal. In fact, this would be a problem I would have asked my pre-cal students on exam 2. Give me all the general solutions to this equation. So I know that at 0 and pi it's true, but there's infinitely many places, right? It's actually at 0, at pi, at 2 pi, at 3 pi, at 4 pi. You could also go negative pi, negative 2 pi, negative 3 pi. So how do we say that in mathematics? We say t is equal to any multiple of pi. K pi or n pi is usually what books will use. I'll use n pi. So it's understood here that n is an element of the integers. Integers. That can be positive or negative, right? Double struct z, integers, we talked about that. So n can be 0, 1, 2, 3, 4 forever, or it could be negative 1, negative 2, negative 3. So at n pi, and then where is it vertical? Where it's undefined, which means where the bottom is 0. Where does that happen? That happens at cosine being equal to 1, right? And going back to our unit circle and looking at cosine, cosine is the x-coordinate. Where does that happen? Where's cosine 1? Cosine is which coordinate on the unit circle? The x-coordinate. So when is the x-coordinate 1? At 0. 0 or 2 pi or 4 pi or 6 pi. We have a problem here. I'm hoping you're seeing it. I could have just put 2 pi n pi. Something is messed up here. Not messed up, it's something we have to consider. Yeah, at certain places, something weird is happening, right? Look, would everyone agree that at pi, right, at 3 pi, at 5 pi, at 7 pi, that my tangent line is horizontal? Yes? The question is, what's happening at t is 0 or 2 pi or 4 pi? Because at 0 or 2 pi or 4 pi or 6 pi or 8 pi, they're both 0, right? Top and bottom? Yes? Y'all agree with that? So I have to address this, okay? What's happening? I know that at all the odds, right? At all the odd pi's, that my tangent line is horizontal. How do I say that? At t is what? Odds? 2n minus 1 pi, right? I know that at all, this is odd numbers, right? Odd integers. So at all the odds, I know that what? Y prime is 0. And I have no problems with that. However, what's happening at 0 or 2 pi or all the even pi's, I need to investigate. So let's just pick one of them. How about t is 0? I would like to know what happens to derivative as t goes to 0? Right? I really need to investigate what's going on. So I need to really figure out what's happening to the derivative as t goes to 0. How could I do that? How about take a limit as t goes to 0? Good. Take a limit as t goes to 0 of the derivative. The derivative was sine t, or sine t, not x, over 1 minus cosine t. Hey, that's a problem I would have given on my Cal 1, or for my Cal 1 students. You get 0 over 0, don't you? Okay. When you have 0 over 0, L'Hopital's rule, right? L'Hopital's rule. Use L'Hopital's rule. It's the limit t goes to 0 of take derivative of the top. What do you get? Cosine t, derivative of the bottom, sine t. And now what do you have? 1 over 0. What does the limit, what happens if you get 1 over 0? Fixed number over 0. It becomes infinite. So this is going to be approaching infinity. Actually, it could be positive or negative because it depends on which side of 0 you come in from. So that nails down, I know what's happening at all the even pi's. It's becoming infinite. So my conclusion here is that when t is equal to any even multiple of pi, 2n pi, that y prime is undefined. Or if you'd like to say, the tangent is vertical. Questions? Back to the picture. Now, unfortunately, my x-axis here, right? Remember, the x-axis is not time, right? Do you all agree with that? Because this is a parametric curve, so x-axis is not time. But let's look here. What's happening at, we said all the odds. What's happening at pi? That's where I am at pi, okay? How about 3 pi? Here. Got it? How about 2 pi? Infinite expression 1 over 0 encountered. Mathematica doesn't know what to do. Oh, I put 32 pi, but let me see if, still going to have an infinite, but do you see where I am? So going back to playing this, remember we were saying it's going to become infinite? This is what? Negative infinity, positive infinity. You see where it switched? It's like, here it is, it's a negative number, infinite negative number, and then all of a sudden it switches to positive infinite number. That's why that limit from both sides was different. Positive infinity from one side, negative from the other. It all matches. It's happening at the actual cusp here. Your derivative is undefined. If you go any infinitesimal amount to the left of it, your slope is negative, and it's a huge negative number. You go any infinitesimal point to the right of it, which is, this is 2 pi, then it's going to be a positive slope. But at there, undefined. Okay, I hope that all makes sense. Yes? Okay, I only have 20 more minutes. I really wanted to show you polar curves. Let me look at your review here. I think I'll show you polar curves. Because there is some more calculus we can do here. On page 510, they give you a formula for the area of a parametric curve. And then under that, they give you the formula for the arc length of a parametric curve. I won't ask you that on the test, all right? But I'm just saying later as you move on and do more math, you'll see, I think you'll be able to look at those and pick them up pretty quickly. It's not anything crazy if you follow through those examples. That's why if I don't ever get to this section, I'm not too concerned, because usually by the time you do see it, you're like mentally mature enough to pick it up pretty quickly. In fact, like in a Cal 3 class, You do parametric curves, but instead of having x is equal to a function of t, y is a function of t, you actually have x is a function of t, y is a function of t, z is a function of t. So now you're in three-dimensional space. So you're drawing a curve in three-dimensional space instead of a curve in two-dimensional space. And then later after that, you say, instead of having a function that's a parameter of one variable, you have a function which is a parameter of two parameters. So instead of t, you have two different things. And then with that, you can draw surfaces in three-dimensional space. But it's all an extension of this. We call them parametric surfaces. So if you think about like something as simple as a cylinder is a surface, right? You could look at this as being a bunch of circles drawn, right? Stacked on each other. I can draw a circle with a parametric curve. All I have to do is change the height of those curves. But you could also look at drawing a cylinder by drawing a bunch of lines and just drawing those lines around a circle. And so you have one curve, one part of the function draws the circles, the other one draws the lines, and together they draw the surface. That comes later, though, much later. Okay, so now I'd like to talk about polar curves. Polar curves are very interesting. They're kind of strange, all right? So I have a little demonstration here for you. I'll save that. See if we can make sense out of this. All right, so the red dot here represents a point xy. So normally, you know, we have the origin, we have the x-coordinate, then we have the y-coordinate, yes? I just showed you a little while ago that if someone gives you an x, right, if someone gives us an x and a y, I should be able to get to that same point by going out a certain distance. Let me move my x a little bit. Let me move it here. Okay, I should be able to go out a certain distance and then rotate through a certain angle. Let's say right about, I'm missing it. Why am I missing that? There. And then bring my radius back. You get the idea, right? So that x-coordinate and that y-coordinate could also be gotten to by rotating through a certain angle and walking out a certain distance. Yes? Okay. So normally we have the xy plane. We imagine there, like if you draw grid lines, like these are all your x values, these are all your y values, then everything is like little squares all over your plane, right? You move a little x, you move a little y, everything runs perpendicular to these grid lines. Y'all agree with that? Change x, you go this way. Change y, it's straight up. Well, we have a different coordinate system, which is polar coordinates. And the way polar coordinates work is instead of the two things being x and y, right? X is left and right movement, y is up and down movement. We have two other variables that we use, r and theta. Theta tells you how much to rotate. R tells you how far out to walk. Okay, so two different concepts. In Cartesian coordinate system, x and y, x is left and right movement, y is up and down movement, Cartesian. Polar coordinates, theta is rotation, r is distance from the origin to a point. All right, so for every point in Cartesian, there is a corresponding point in polar coordinates. And so there is a relationship between these two, and here's the relationship. If I have a point, xy, I can always draw a line to it, which creates a radius. See, I'm not on the unit circle anymore, so I'm going to call that r. And I always have some angle that corresponds to that. And so, again, if we drop a perpendicular and create a right triangle, we have some new relationships. What are they? Cosine theta is what? not just x this time, but x over r, and sine theta is y over r, which means that x is equal to r cosine theta, and y is equal to r sine theta. I'm boxing these because these are what we call the conversion equations. If you want to go and take something from Cartesian, okay, xy to polar r theta, these are two of the equations that you can use. Now the other relationship we have, there's two more relationships that we like to write down, is the Pythagorean identity off this right triangle. We know that what? X squared plus y squared equals r squared, so that is a relationship between Cartesian and polar. And then, one more thing, I know that theta is arctangent of y over x. And that's because what's tangent theta? Y over x. So arctangent of theta, theta is arctangent of y over x. So these are the four major equations that we have from Cartesian to polar coordinates. So that's just to give you an idea that, look, we're going to be looking at a different coordinate system here now. These are the relationships, but the picture is this picture I showed you. Notice that in a polar coordinate system, since everything is not perpendicular, the things that are important to us, the angle, sorry, I'm pointing to nothing here. What's important to me are the r and the theta, right? So if let's say I fix a theta, just fix a theta. Let's say pi over 4 here. And I say let r be anything. What's it going to draw? A straight line, isn't it? What if I say don't fix a theta, but fix a radius? So fix your radius, let's say at 1, 2, and draw, and let theta be whatever it wants to be. What's it going to draw? A circle, right? You see that? Do you see why? This is what graph paper looks like for polar coordinates. That's what graph paper looks like. And I provided you a couple pieces. That's probably too much, but go to that table with it. Take like 2 of these, 2 each. I wanted to practice graphing a couple of things polar, and then we'll use our calculators. I promised you we have 10 minutes. Okay, on your first one, I forgot to tell you the way we write polar curves. Polar curves are written this way. How do you write parametric curves? Parametric curves, x is a function of t, y is a function of t, right? The way you write a polar curve is this. R is a function of theta. Or you could possibly have theta equals a constant. I'll say a different function, g of r, a function of the radius. Either your radius is a function of theta or your theta is a function of the radius. But this is the one that's most commonly used, right here. So I'm about to give you an example, and we're going to graph it. I would like for you to graph r is 2. This is trivial, okay? But let's just do it real quick. So what that means is on your graph paper, right, you have these like circles in there. You need to label what radius 2 is going to be to you. So maybe you go 1 here, and that's 2, right? This is just saying your radius is always 2. And your theta can be whatever. So let your radius be fixed at 2, and now change your theta and keep changing your theta and keep your radius. You can draw a circle radius 2. So because of what we're going to do in a second, I want to make sure you really understand this. When theta is 0, I've gone out 2. All right, this is 2 for me. That's what 2 is. All right, and now I'm going to let theta change. I'm going to let theta change to pi over 12. What is the radius of pi over 12? Still 2, right? What's the radius at pi over 6? Still 2. At pi over 4, still 2, right? If I do that the entire way around, then I wind up drawing the entire circle, right? Okay, let's try the next one. I want us to graph r is equal to cosine t, or cosine theta. What does this look like in polar? So what we're going to do is we're going to start plugging in some values, all right? Help me out. This is theta, this is r, right? Give me a value of theta. How about 0? What's cosine of 0? Is 1, right? Do you all see that? R is cosine theta. I plug in a value of theta. I walk out this far. So what that means is when I'm aiming out at 0 for theta, which is this direction, I will walk out how far? 1. So I put a dot there. Got it? Put my dot here. Now we need to change the theta. So let's let theta increase. How about to something we know? How about pi over 6? Okay? So what you would do is you would go to pi over 6, right? Is what I'm going to plug in. That's 2. And then cosine of pi over 6. What's cosine of pi over 6? Root 3 over 2. Square root of 3 over 2. What is that as a decimal? Less than 1? Yeah. What is it though? Someone do root 3 over 2 real quick on their calculator. .866. Okay, approximately .866. So how am I going to do that? What does this mean? It means I rotate, right? I rotate by pi over 6, and I walk out .86. So what the hell happened? Did I move my graph? How did that point get moved? Oh, I moved it and it scaled it. It changed. Okay, this was at 0, right? Remember, that's 1, isn't it? So .86 is smaller, right? But you rotate to pi over 6 and draw it. Do y'all see that? So now you're here. With me? Now, if I connected the points between there, just so you know, that's what they would have looked like had I connected them between there. I don't have the time to fill that all in, but do you see it? Okay, now go to the next one. How about, I don't know, pi over 3? Let's do pi over 3. So pi over 3, where would you be? Cosine of pi over 3 is 1/2, which is 0.5. So that means I'm going to rotate by pi over 3, which is here, and I will walk out how far? 1/2, which should put me, I believe I'm measuring that this is 1, no, this is 0.5, and that's 1. So I believe it's going to be here on my graph. Now, I don't know, it's going to look weird if that's what it is. Yeah, that's it right there. Okay, now let me connect the other ones because, again, you can't connect those. This is what they would have been. You still following me? Okay, what's going to start to get interesting is what happens when we get to pi over 2. Okay, what do we get at pi over 2? Cosine of pi over 2 is 0. So that means I'm going to rotate till I'm pointing which way? Rotate till I'm pointing straight up and walk out how far? 0. That means I'm here, right? At the origin. So it's going to look like this. Okay? That's where I am. Let me move myself around here. Oh, there. Okay, this is where it gets really interesting, all right? Let's just go to 3 pi over 4, right? 3 pi over 4. What's cosine of 3 pi over 4? Cosine of 3 pi over 4 is negative root 2 over 2, right? Negative root 2 over 2, which is about negative 0.707, something like that. So that means I'm going to rotate to what angle? 3 pi over 4. And I'm going to walk out how far? Negative. Oh, you mean go that way? Okay. Negative what? 0.7 something. It's going to put me like right in here. Oh, no, that's 0.5. 0.7 is like right there. So I'm actually going to be down here now because it was negative, right? It's the opposite. So the radius could actually be negative here. And if I keep doing this, I'm off a little bit there. That's where I should be. It's going to be a circle, isn't it? So does everyone understand that as I'm coming around this direction, right, like this, it's drawing them backwards? Now, hold on a second. Where did I stop? Where did I stop? I drew the whole circle, didn't I? I actually drew the entire circle, and all I went to was from 0 to what? Pi. I actually drew the whole thing just rotating from 0 to pi, and I drew the whole circle. So if I keep going, what's going to happen? It's actually going to draw another one on top of itself, but you're not going to see it. Look, so see how my bar stopped here at pi? If I go to 2 pi, you see it draw it again, but it's on top of itself. Oops, like that. See that? Do y'all get that? Yes? Would you agree that I could have also drawn this thing by restricting my domain not just from 0 to pi, but I could have done this. 0 to pi over 2, right, would draw this part. And then if I would have gone negative pi over 2 down here, it would have drawn the bottom part. So if I would have gone over there on my domain from negative pi over 2 to pi over 2, I actually would have drawn the same circle. Yes? All right. There's more here that you can play with yourself because I'm running out of time. 1 minus sine t was the next one I was going to do. Or no, 1 plus sine t was the next one I was going to do. And it would have looked like this. Okay? The next one I was going to do was 2 minus sine t, and it would have looked like this. And then this one was cosine of kt, and I was just going to change the kt. So cosine of 1t would have been the circle we just drew, right? But if I change that to 2t, look what happens. Oops. It draws that. And if I change it to 3t, cosine 3t, it's this. 4t, 5t, 6t, 7t, 8t, 9t, 10t. And the only way you'd know that is to draw it. So imagine you're like rotating by these angles, right? And you're going out and it's coming back in and going back out and coming back in as you're going through these angles. Because look, it's oscillating. It's giving you all of the cosine circle drawn in a smaller period of time. Do I have this animated? Yeah, let me back it up a little bit. Hold on. Let me just do those. Watch. If I take my theta and play this, watch the way it draws this. I need to slow it down. Okay. It's coming like this, going like this, going back around, starting, coming like, it's too fast. I know what I can do. Where's my theta? My theta is here, 36. What I'm trying to show you here is how it draws it. Because your instinct might be telling you that the way it's drawing it is going like this. Like that. That's what you may think. But remember, cosine is going to be negative at some points, right? So there. So you see it? Here we go. It's going to go like this. And then there's your negatives. And then like this. And then like this. Okay? Does that make sense to you? So if in polar coordinates, which we're not going to have time for, if you want to know the area of one of these leaves, then you're going to have to restrict your domain to where, you know how you have limits of integration? Okay? You'd have to restrict your domain to just the angles that would draw that piece. Just the angles that would draw that piece, which would take a little bit of investigation. So it's not as simple as just, oh yeah, we just, 0 to 2 pi. You have to look at it a little bit. So we're not going to get into it. I mean, unfortunately, we can't go any further because we just don't have enough time. This is Cal 2, right? Who's taking Cal 3? Anyone taking Cal 3? No one? Cal 3? No, maybe? Okay. All right, it's okay. I mean, am I not teaching it next semester? Oh, I didn't realize that. Oh, yeah, that's right. I try. Well, I wanted to show you. I can show you right here. Well, all right. You'll just have to trust me on it. I'll tell you what it is. It's a problem in Cal 3 where you take a sphere, right? You take a sphere, and what you want to do is you want to drill out a hole from the sphere. So you come in here with the drill bit and you drill out a hole. But let's say you drill out a hole, not right through the center, but off-centered somewhere over here. And you drill out that hole, right? Take your sphere, you drill out a hole, but it's not centered. And the question is, what's the volume of the sphere that's left? So what you wind up doing is you wind up looking at, basically in the two-dimensional plane, you look at this circle on the ground, right? That circle on the ground. So if I cut the sphere in half and looked at it from the top, it would look like that, wouldn't it? This right here, this circle is a polar region. You can draw it with the polar curve. Just like we just drew cosine x, right? Or cosine t or theta, whatever, just drew that, drew a circle. I can draw that, and then you do a bunch of calculus in polar coordinates. God, I can't shut up. I'm sorry. I know you want to talk about the exam. I have a review for you. I know. Just bear with me. I forgot to show you one thing. Sucks to be you right now. Wrong class. No, there was one thing I wanted to show you on this cosine. We saw it drew a circle, right? Okay, watch this quickly. Square both sides of the equation. right? Okay. How should I do this? Let me do it a different way. This circle right here that we drew, all right? Let me do it this way. This circle, it went out to 1, didn't it? That means this is halfway. Yes? Do you remember the equation of a circle? If it's centered at HK? Do you remember that formula? Okay, if I use this formula, what's the center? 1/2, 0, right? So this would turn into x minus 1/2 squared plus y squared equals, what's the radius squared here? The radius is 1/2 squared, you get 1/4, right? Now if I FOIL this thing out, I get x squared minus, what's a 1/2x and a 1/2x together? It'd be minus x plus 1/4 plus y squared equals 1/4. And the 1/4 cancel, right? And what you get is x squared, can I write it this way, plus y squared minus x equals 0? Okay, convert it to polar coordinates now. What is x squared plus y squared? What is x squared plus y squared in polar coordinates? It's r squared. What's x in polar coordinates? R cosine theta. Oh, crap, I'm sorry, I didn't see all that shit up here. All right, this is r squared. This is r cosine theta. Factor out an r, and you get 2 possible equations. R is 0, and r is what? R is cosine theta. What was the polar equation of this? R is cosine theta. What I'm showing you is how you can convert a Cartesian circle into a polar equation. All right, so that's what my Cal 3 class has to do. They have to take, I just draw the picture and just let them do all the math behind it. Okay, let's talk about the final. Let me give you the review. Here we go. So the best way to review for this test is to take all that homework that you brought today and take this I'm giving you. I'll have a few. If there's extras, just pass them along, pass them back this way. Just right there, yeah. What do we have here? 24 problems. This is a good, I think this is a good review in terms of like, I'm probably not going to deviate too much from this. But then I wouldn't be, you know, I wouldn't want you to be all pissed off if I put a problem like a homework problem on there too. You know, I mean, you should be looking at everything. First problem, area between a curve. That involves, you know, you drawing the regions and things like that. Find the volume of a solid obtained by revolving a region bounded by a curve around an axis. So that's where you draw your region. All right, you draw your region. It's the x-axis, so you have your axis of rotation. You take that rectangle, remember this, rotate it about the x-axis, draws you this thing here, washer, and then we had the method of washers. You had a formula, right? So you want to make sure you have all your formulas. So what can you bring on the test? I let you have a formula sheet on your midterm, right? You have all your formula sheets and then one extra sheet. Is that what I did? You can bring that extra sheet again, and you can bring another extra sheet. That's fine. All right? So there's no complaints about I didn't have the formula. I mean, you should have them. Find the length of a curve. Notice I put next to each of these what section they're from. Okay, so you can go back and take a look. Find the length of the curve. Pardon?
I thought you said we did 7-1 to 8.
7-1 to 8. Is there stuff here from? Oh yeah, you can scrap that 6 stuff. Sorry, I didn't see that there. You can scrap the 6. Get all mad. Scrap 5 and 6. By the way, those are integrals, infinite integrals. So number 5, you'd have to do partial fraction decomposition. Then you would have to integrate, and then you would have infinite limit. You'd probably have some natural logs in there. Number 5, you have a discontinuity inside your integrand at 2. Just pointing that out. All right. 7, I give you a series, and I ask you to find its sum. If I ask you to find its sum, that means it's probably either geometric or collapsing, right? 8, find this sum. That means it is a sum, right? It adds up to a number. That's probably what? Number 8 is probably what? Collapsing, probably telescopic, right? So you'll have to do what? Partial fractions. Okay, 9, I'm telling you, use the integral test to determine if this converges or diverges. So I'm telling you to use the integral test because I think you need to know how to use it for this exam, which means you have to show the two conditions, positive, decreasing. All right, use the comparison test. So I'm hinting to you what test is going to be utilized here. Number 11, use the limit comparison test. So I'm asking you to do a different test for the same series. So on number 10, I say use comparison test. On number 11, I say do that same one, this time limit comparison test. Just again to show that you know how to use both tests. 12, use the alternating series test to determine if it converges or not. 13, use absolute convergence test to determine convergence or divergence. And now we start getting into the power series. So 14, find the radius of convergence and interval of convergence. You can scratch radius. I never asked you for radius on anything. I always asked you for interval. If you got the interval, that's more than I need. So, or the interval is what I need. The radius is, it's all right if you don't have it. So how would you do 14? What test did we use for finding intervals of convergence? Ratio test. Every single time, I don't know if y'all noticed that, every single time we did an interval of convergence, it was always ratio test. And we wanted that ratio to be less than 1. And that gave us our interval, right? Okay, number 5, find the power series. Find the power series for this. When I say power series, I mean the summation, blah, 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 whatever it is. What would you use for that? What do you think? How about that 1 over 1 minus u? Remember that formula for 1 over 1 minus u? 1 over 1 minus u is equal to summation u to the n as long as the absolute value of u is less than 1. That was that one we used repeatedly where you had to like, this one you would have to like factor out a 2 and make it look right and then rewrite it in that series. Number 16, you would need to do what? Realize that what you're looking at there is the derivative of something you do know the power series for. 1 over 1 minus x. Negative 1 over 1 minus x. So trust me, I did those in class, and I mean, there's something there for those. You can go back and look at them. Okay, number 7. Find the Maclaurin series for f of x equals x cosine x using the definition, not the table on page 484. Yeah. So that means you need to take the derivatives, you know, the 0th derivative, first derivative, second derivative, third derivative, and find a pattern, and then rewrite it in its Maclaurin series. Okay, 18, find the Taylor series. So same thing. You need to take the derivative at a equals 3. The good thing about that problem is that the derivative of e to the 2x is always it's going to follow a pattern. Okay, you have to be careful. That 2x up there is going to make it different than what we did in class, because in class we had e to the x. So derivative was just e to the x, e to the x, e to the x. Here, when you do derivative, it's going to be 2e to the x, then it's going to be 2 times 2 e to the 2x, and then 2 times 2 times 2 e to the 2x, and you start to see that there's a pattern there, right? All right. 19, approximate this by integrating the first 3 terms in the Maclaurin series. So on 19, you are allowed to use the table on page 484. I don't know. Did I do that one? I thought I did sine of x cubed. I did sine of x cubed from 0 to 1. I didn't do e to the negative x squared from 0 to 1. But what I did do was we did write out the terms of the series for e to the negative x squared. So do y'all follow me? On number 19, to come up with the power series, the Maclaurin series for e to the negative x squared, you do not have to generate it using the derivatives like you did in numbers 17 and 18. On 19, you can go to the table on page 484. Or because you're all Cal 2 students, you've all memorized at this point that e to the x is 1 plus x squared, or x plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, right? And then if I replace that with negative x squared, then you have the Maclaurin series there. If you can find a way to get that table printed out, you can bring it to the test, in addition to everything else, all right? You know what table I'm talking about? Okay. But be careful. You can't use it on numbers 17 and 18. That one you have to do it by hand. All right, number 20. Given a set of parametric equations, find dy dx at t equals 1. So you find the derivative, then you plug in 1. That's what we just did today. Number 20 was the same problem. No, I don't know. It printed twice. Sorry. You can't do anything else on there. 21, 22, 23, 24 we didn't do. Right? We can't find the area of a curve. We didn't area of a parametric curve. Can't find the length. Yeah. Look at that. 1240. Look, we're done. For those of you who are interested, because I told you to bring your calculators, if you go to your to the mode and you switch to polar mode, all right? If you switch to polar mode and you go to graph, it'll have like R1 there, R2 there, R3 there. It's asking you to put in a polar function. So if you put in cosine, I believe it's going to use t for its theta. If you do cosine t and you have it graph, it should draw the circle we just had. And remember, the window feature on your calculator allows you to adjust the variable. So you can adjust t between 0 and pi or whatever you want. And then the parametric, we did that before, right? If you do parametric mode on your calculator, it brings up x1, y1, and those are your parametric equations. Sorry, I told you to bring them. What about your grades for your homework? I'm going to take my calculator before I forget it. Homework? Yes? If you have it, then raise your hand. Okay. How are we going to do this? It's 12:40. Anyone have to get out of here right now, like in a hurry? Yes? Okay, let me see what you got real quick. It's going to be a quick thing. I just want you to come up to me, just breeze through your homework, just so I can take a look.